Yes, so good morning, students. And today I will be teaching Word2Vec, Skipgram. And there are a couple of things we're going to do today. First is loading data. So we're going to be loading some very small data to make sure we don't spend too much time on this, but make sure that my code can actually work with any CSV file, which will be on your assignment anyway. And then on the second, we're going to prepare some train data and then do some model and perform some training and plot the embeddings to know that things are closer or not, and then do some cosine similarities. All right. Without further ado, I think we should import something first. So we're going to do import numpy or something. Let me make my screen bigger. Yep. In that way, you guys can see clearly. And import torch. Import torch.nn. That's nn. Yep. So numpy is for matrix manipulation. Torch is mainly for neural network, and matplotlib is mainly for plotting. All right. So the version I'm using is this, and okay, I did some mistake here. All right. And then my matplotlib. All right, give me 1 second. All right, so those are the versions that I use in my program. All right, and then without waiting, we can start loading some data. All right, so I have prepared some data. So let me type first. So it's a list of documents, and each of the documents have just 3 words. Banana, fruit, apple, dog, cat, animal, cat, animal, dog, and lastly, cat, dog, animal, right? So the idea here is that you can imagine that each of this is representing a document, and inside it has 3 words, which just doesn't make sense, but this is just a simplified version. And then what I'm trying to simulate is that this is a center word and surrounded by 2 outside word. In that case, banana, the embedding of the banana should be close to the embedding of apple and fruit after training, right? Of course, this is strictly within the window size of 1, right? So anything on the left and the right side within 1 space is actually the associated word. If I add 1 more word here and I want them to associate with a center word, then I have to change the window size to be 2, right? Which is a hyperparameter we have to figure out, right? If you work in your assignments, you have to maybe adapt that accordingly. But anyway, what I'm trying to do is I want to make sure these 3 words are associated with one another, but they are very far from these 3 words, which are also closer to one another, right? So that is what I'm trying to simulate here. All right, so the next thing I want to do is I want to split them into words. All right, and so we can do something like this. All right. So this is basically a very basic step that we all NLP people do. And this step we call this tokenization, right? Of course, there are so many ways in which you can tokenize words, but today, since we're just beginning our class, we're going to use the most basic tokenization method, which is basically based on words, right? But there are a lot of subword tokenization methods that are superior than this, right? Because English word is actually can be represented by a lot of root words instead, right? But anyway, I think we're gonna be fine sticking with this. Right. Then the next thing we're gonna do is since computers don't understand words, then we're gonna do something called numericalization, which is simply assigning each unique word a number, right? So there are things we need to do, that is find unique words, and then assign unique number, integer, right? It must be integer, obviously. So the way we're going to do is first we're going to flatten everything, all right? So we're going to do, we're going to create a function called flatten, right? Which gonna take each of these lists, right? And then for each of these lists, sublists, we can take each of the item, right? And this is going to be basically list comprehension. And then we're just going to return the item, right? And I'm going to call this a function, right? So we're going to say lambda L, right? So the input to this function is basically L, which is this, right? I'm going to get the sublist inside here and get each of the item here. And then I'm going to now pass in this thing and pass in our corpus, right? And then well, we can actually try to see what is happening in this button, and it gave me a lot of unique words. Now I'm gonna apply set, which gonna give me only the unique words, and then of course I'm gonna apply list, right, so that I can get a list of words that I'm gonna work with, and I'm gonna call this vocabs. Vocabs is a very common terms in which NLP people call, which refers to all the words we have in the system, right? And anything that is unknown, we usually call this right? Just for your information. All right. And once we do a numericalization, maybe we're gonna create some handy mapping between integer and word, right? Which will be useful for our functions later on. They're going to create a dictionary, a lookup dictionary, and what it's going to be for index, we enumerate vocabs, v colon idx, like this, right? In that case, once we do this, we can do something very cool like this, right? We're going to call animal, right? And it's going to give me the index of that, right? If I call dog, you're going to say that dog is actually 3. Similarly, I think we should do for index to word. But before anything else, I want to do something. I want to add unc. Right. And I also want to make sure that I have this in the Word2 index. And I think I have to count, right? 0, 1, 2, 3, 4, 5. So the next one, 6. All right, great. Now I think we can create the index to word. Similarly, we can do index to word. Basically for KV and Word2 index.items. Okay. And we're gonna just switch V and K, right? Then we column K. All right. So once we do that, I think now we can actually try this, right? Index to word. And it's a very nice mapping between integers and animal. And of course, I can do something like, hey, what is 5? And that is apple, right? So I think that is a good start. We did all the loading data. All right. So now we're going to close this and we consider this done. The next part we're going to do is actually preparing our training data. And basically what we have to do is create pairs of center word and outside word, right? And we need to create this pairs for each of the outside word, right? With that center word. So there are many pairs, right? So what we're going to do is, so we have to basically loop each corpus, right? And we're going to need to loop each document, right? And then we're going to look from the index of the first word, right? Actually, not the first word, the second word, right? Because you cannot associate the first word with any outside word because it will be, I mean, there's no word on the left side of it, right? So you should start at the second word and similarly until the second last word, right? And then you just assign the center word. What is the outside word, right? And outside word is if we use window size of 1, we're going to have 2 words, right? That is associated with the center word, right? And finally, we append for each of these 2 outside words. So we're going to append to a list, right? Containing basically something like center word, outside word, right? Outside 1, and also the center and outside 2, right? So I think that should be it, right? So now we're gonna try to create. Firstly, we're gonna create a list that's gonna contain, and I'm gonna call the Skipgrams. And now I'm gonna loop to the corpus, right? And I need to loop each document, right? And what I'm gonna do is I'm gonna start with for I in range, because yep, I mean for each of the sentence, maybe we're gonna call this doc, right? Once we get each of the document, we already have the words, right? So we're just gonna look from the second word, right? So the range is basically, it starts from 0, so it will be 1, and this is going to be length of doc minus 1, right? Which going to give us the second last word, right? And then based on that, now we can get the center word, right? Give me 1 second. Okay, I think the indentation is a little bit weird, so I'm going to put back. And the center word is basically center equal to doc I, right? So because this is already starting at position 1, then this is probably the center, right? And then the outside word is basically doc I minus 1 and doc I plus 1, right? And I think we can put it in tuple, right? So that would be the outside word of this, right? And then finally, we're gonna loop each out in outside. We're gonna append skip to the Skipgrams. So center, out, each out. All right. And I think based on this, I think this is pretty much done, right? Now we just print out the Skipgrams, and now we can see that we have very nice center word, outside word, center word, outside word, right? You can see that each of the center word has 2 word that is associated. All right. All right, so now we got the skipgram. So we have to modify a little bit. Firstly, we know that we cannot let it return words like this, right? Because computers don't understand words anyway, right? So we're gonna put our word2index right here. So this is gonna be nicely converted to integers. All right. So now everything looks using our integers. And the next thing I'm going to modify is that I want it to serve as something like a data loader, in which it randomly pick some of the samples here. I call this one of the samples, right? In which this is the target and this is the label, right? And so we want these two embeddings when they dot product together to be very nice, right? But anyway, what I want to do is I want to randomly choose these samples and train, right? And not use all the samples, right? So to do that, I'm gonna create I'm gonna randomly select. So I'm gonna use a randomly np.random.choice. Range length of the skipgrams, right? And how many I want, right? That would be determined by a hyperparameter I call batch size, and I'm gonna use replace equal to false, so that it doesn't keep using the same number in that batch, right? Since I have this batch size parameters, I may want to create this as a function, all right? So I'm gonna put all this. I'm gonna create a function called random batch, and I'm gonna input some batch size and corpus, right? And I'm gonna indent this in. All right. So that this will be determined by some people as the user, right? Now that this is the index, right? The random index. But before anything else, why don't we just try this and see whether it really works? Random. Let's say I want 2 batch, and I input the corpus, and let it return the random index. All right, and I got actually 4 and 10, right? So great. So that means that it's pick the sample 4 and sample 10 from this corpus, right? But we actually doesn't want it to actually return the index. We want to just return as a samples that is ready to send it to the neural network. So let us do something more here. So we're gonna put here random input. Actually, we just call this inputs to make it small, labels equal to, all right. And we're gonna say that for index and random index, inputs append. What are you gonna append? You're gonna append skipgram, right? Of index 0, right? So 0 is basically referring to the center words. And similarly, we're going to do this for the labels. So we're going to change this to labels and put this one. All right. And finally, we're just going to return this function np.array. Yeah, it's better we convert this list to np array so that it will be very handy when we convert to PyTorch or anything. So NumPy is nice. And then np.array labels. All right. So once we did that, I think we get a very nice batch of so what this means is that the inputs is 5 and 2, and the output is 1 and 3, right? So given the center word of 5, the outside word is 1, and this one is outside word is center word is 2, and then the outside word is 3. All right, so I think we are good to go. So now I think we are done on this part. The next part is actually creating the model, right? So creating a model is actually very straightforward. So we're gonna start right now. But before anything, I think there's one more thing I want to do here, which I forgot, is basically printing the shape and allow you guys to actually check the shape, which will be very useful when we actually design the model. So we're gonna do input label. Oh, we can use x and y. X, y equals that, right? And we're gonna check x dot shape and y dot shape. All right. So I think actually, why not we just do separately? Right. So that was 2-1, and that is 2-1, right? So the shape here is a batch size, right? And 1. Similarly, here is batch size 1. Okay. So this would be the typical input to our neural network that we have to take note of. So now we can close this. Now we can go to the model, right? On the model, we can create our class Skipgram and inherit NN.module. So this is basically a neural network, right? And then there's 2 functions we actually need to take care of. And the first one is init, and the second function is for. And in the forward, we have to enter the center word, the outside word, which is basically the x and y that we get in the training data, right? And then we also need all the vocabs. All right, which will be used, I guess, around here. All right, and then we're gonna do that. So the first thing we're gonna do is basically once we pass in our x and y, which is basically a number, right? That we actually saw here is basically a number, right? Right. So once we pass in 5, we have to do something, right? Because according to this equation, the u and v, the outside word and the center words are vector, right? So basically, we have to create an embedding that represent number 5 and number 1, right? And then dot product them together and put it into exp, right? So we're going to do that by creating using something called nn.embedding. So in the init function, we're going to go super skipgram self dot init, and right here we're going to do self dot embedding for the center word, right? And then we're going to do nn.embedding vocab size and embed size. So what is this, right? So I can actually show you what is this. Very simple. So we're gonna try some just some embedding, right? And then dot embedding. Maybe I'm not sure how many vocab we actually have. Actually, we have 6, right? So why not we do 6? Actually, why not we just print it out vocabs? And I think it's we got 8 limit. Let us just look at what our vocabs and okay. I think we have extra unk. So somehow maybe let me just make sure I delete that real quickly. Okay, I guess I run this twice, so that's why I got 2 unk, right? So why not I just run one time and then it should have just 1 unk. Give me 1 second. So let me close this and clear outputs, restart and run all. All right, great. So our vocabs looks nicely and the length of vocabs is 7. Now that is great. So I'm gonna just simulate that we have 7 vocabs and then the embedding size. Let's try 2, right? So what is this embedding, right? Well, if you try, so basically this is a lookup. It creates a randomly a vector of size 2 for each of this number, 0 to 6, right? But of course, this is still very confusing, right? So I can try some number A, which is a torch dot long tensor, and I'm gonna put 2, right? So this is a tensor of number 2, right? And maybe I can also check the shape, and it's 1, right? Okay, great. So what I'm gonna do is I'm gonna just pass this embedding inside A, and it's gonna return me a very nice a vector of size 2, right? So these 2 numbers is a vector that represent A, right? And of course I can try 3, right? 4, 5, and 6, and 7. 7 will be errors, right? Because it's out of bound, right? Because 7 means that you only have 0 to 6, right? So basically, it just randomly initialize some vector of size 2 for each of the number from 0 to 6, right? And through our training, this vector will change, right, to make it better represent the words we are trying to represent, right? So this is basically the primary goal. We want to learn this embedding that can best represent the words that we have here. Okay, so that's great. And so now we have this embedding. And of course, since we have this, so we gonna put this into some that users can specify. Similarly, we're gonna do this for outside words. All right. The reason why we need embedding for center and outside is because sometimes some of the word can be center at the same time, also can be the outside word, right? So by learning when it's a center word and when in the context when it is outside word and through many texts, and then once we learn everything, we can average this to embedding, right? To best represent that word, right? So that is the way we're gonna do here. So once we have that, now we are ready to do this forward function, right? So we're gonna send our self.embedding center. We're gonna send our center word right inside, and we're gonna retrieve some kind of embedding, right? Some vector, right? We're gonna call this self center embedding. Similarly, we're gonna do this for outside. Yeah, and then we're gonna similarly do it for vocabs. Right, we're gonna talk about this vocabs real soon because you guys never see this all vocabs thing, but we're gonna do this after this, right? So you guys can quickly see what is this. We're gonna call this all vocabs embedding. So as a rule of thumb, it's very important that we know the shape of all this thing, right? Because shape is the only thing that can make us keep track of things when data is very big. So what we can do is, instead of putting a, maybe why would we not put x, right? And I think x is a numpy, right? So what we're going to do is we can do something like this, right? So we're going to do x tensor, and perhaps we can put x here. X is, for those who forgot, x is actually written, is right here, right? So now we can input this x tensor, right? And we're gonna get a very nice shape, and we're gonna check the shape. And the shape is basically 2, 1, 2, right? So let me just take a look. What is the shape? 2, 1, 2, right? So what is this, right? So this is basically batch size 1 and embedding size. All right. All right. So now, so this is the embedding size. So now we know that this is basically a batch size 1. It makes sense, right? Because previously the shape is this, and once we embed, we got this embed size, right? This is similarly that, right? But for this one, because it's all vocabs, then we'll change this number to actually vocab size, which contains all the vocabs. Now, to do this equations is a little bit challenging, so we have to refer to this equation, right? So I'm gonna just real quickly copy this equation, right, and paste it right here, right? And I'm gonna press M here to make it mark down, right? So we have to multiply, basically perform a dot product between the outside word and the center word, and then perform exp, and then divide it by some lower terms, right? So the top term is basically equal to the outside word, right? Dot BMM, right? What is BMM? BMM is basically dot product, but B stands for batch, so it will perform matrix multiplication batch wise, right? Basically ignoring this batch wise. This one embed size will be dotted with this one embed size, right? So that is BMM. So now I'm gonna do center word, right? And since they are in the same shape, we have to transpose this 1 and 2, right? 1 and 2 referring to this, right? So embed size will be here, and 1 will be here, right? 0, we don't touch 0 because 0 is a batch size. Of course, you may wonder, like here you say U transpose and V, why I'm transpose center, but it's the same, right? Because two vectors, when they multiply, they are the same in any order. Yeah. All right, and then once we get that, so let us make sure we understand the shape here, right? So firstly, we got this batch size, right? Dotted with the transpose version. Right, and this should give me something like batch size, right? So this embed size will be canceled with this embed size, and gonna get 1 and 1, right? What I'm gonna do is I'm gonna squeeze, I'm gonna delete this dimension, all right? and then just leave with that, right? Which will be useful when I do the probability. So I'm gonna squeeze this into batch size 1. All right, so I can do that simply using a function called squeeze, and which dimension I want, right? The dimension I want is 2, so I just put 2 right here. All right, so I think we're good, and maybe just delete this to make it having no strange colors. And then of course I'm gonna do I need to do exp, right? Because there's an exp right here. So I'm gonna say torch.exp. Okay. Now let's do the lower term. So the lower term is basically all vocabs. Embedding. Oh, by the way, I think I spot some mistake, right? Actually, right here, I should use all this embedding, right? Not actually. So this should be that, and that should be that, right? Okay, great. And now for the all vocabs, which is represented by this UW, right? I will be taking that and then dot VMM center embedding transpose 1, 2, and similarly I'm gonna squeeze this into 2. All right, and I think right here. Okay, great. And then of course that should be it, I think. All right, so instead of summing, I just create an embedding of everything and then just dot product here, right here. So let us check what is the shape right here. So right here, our vocabs is this, right? And we dot with embed size comma 1. So then once we do that, embed size and embed size will be canceled, and we only have vocab size comma 1. And finally, we squeeze the second dimension. Now we got this vocab size. All right. Now we have to now sum everything together, right? Because there's a summation sign here. So we have to do lower term sum equal to torch.sum. And of course, exp, we have this exp in front of here, so torch.exp, and then lower term comma, and which dimension we have. So firstly, I need to torch.exp right here, and then I have to say which dimension I have to sum, right? So you can notice that this is batch size, vocab size, so I have to sum across the vocab size, because according to the equation, the sigma indicates this vocab size right here. So I put 1 right here. All right. By doing that, and now the shape right here is batch size 1. All right. And of course, now we can, once we have the top term and the lower term, now we can actually divide them, and that should be it, right? So now the loss function, right? Since we want to maximize this, when we write the loss function, we just put a minus in front. That would already turn the function into minimization problem. Now we're going to do the top term divided by the lower term sum, right? And we we are well aware that when we deal with probabilities, it's best that we use log, right? So log give us a lot of stability. So we're going to put log in front, even though the equation did not. You don't have to worry that applying log will change your numbers, because log is a monotonically increasing function, so it won't matter. And then finally, we're gonna just take an average, right? Right. You may wonder why we need to take an average, because when you basically, this term is batch size comma 1. This one is a batch size comma 1. We log is still batch size comma 1, but to be a loss function, it must be one number, right? So we have to take a mean to create a one number. So otherwise it cannot be backpropagated, right? So we just take an average of the loss between the top term and the lower term. All right. So this one is basically a scalar, right? And finally, we just return this loss function. Actually, this is not a loss function. I would say this is the loss, right? Okay, good. So yeah, I think that is pretty much it for the Skipgram, right? And before anything, before we actually try using this, why not we do some extra steps, right? Which is preparing all the vocabs to be inserted right here. To do that, we can simply call batch size equal to 2 right here. And we're going to create a function called prepared sequence and Word2Index. All right. So right here, what we're going to do is so firstly, I'm gonna, in this function, what I'm gonna do is the way I'm gonna call this is something like this, right? I want to get all the vocabs, and the vocab shape should be something like batch size and then the vocab size. All right. So this is what I want from this prepared sequence. Right. So for those who are wondering, what I'm trying to do is, I mean, this is a very basic function in which I try to just create, turn all the vocabs into numbers, and then just as a tensor, right? So I can actually show you what I'm trying to do. This is very trivial, actually. So what I can do is I'm gonna get the index, right? And I'm gonna take a map, right? So what this map function is doing is trying to take everything inside that list and do something with it, right? And so I need to define a function, W, right, which is basically turning each of the word into number, right? If that word exists, index dot get W is not none. All right. Otherwise, we just return the all right. And for the map, you have to input two things. First is the functions, and then the list that you want to look at each of them and apply this function, right? Which is basically the sequence. All right. And then once I have that, basically this is a list of index of all the things I put it, whatever sequence I have, right? And then once I do that, I just simply return torch.long tensor and the index, right? The reason why I have to turn it into tensor so that it can be put into neural network, right? So this is very trivial, right? And it will be useful when I actually insert into this one. All right, so now so all vocabs equal to prepare sequence, and let's start with the vocabs, and then word to index the lookup dictionary, right? And then this should be it. And now you guys can take a look. What does this all vocabs look like, right? So this is basically a list of things that if I put in this vocabs, then it would return me as a tensor, right? Of course, whenever I insert to this neural network, I have to insert according to the batch number of that, right? So I have to do something to make sure that it has. So I'm going to say expand batch size and vocab size. Vocab size, I don't have this, so I'm going to do vocab size equal to length of vocab. Right. So great. So so what I'm trying to say is that if my X is this, right, and my Y is this, right, I will always have all vocabs that list all the numbers, right, which will be useful when I do all these operations. All right. So I think that is a very nice function. Perhaps I think we can also use this for X and Y, but actually, let's see. I think I did it in the random batch already. Okay. All right. So this is the all vocabs, right? So now before anything else, why not we test our neural network, right? So we're gonna do model equal to Skipgram. Our model is actually named Skipgram. And we have to input the vocab size, right? Which we already have, right here. And the embed size is 2. Yeah. Please don't confuse with this embed size and batch size, okay? And I think that should be it. All right. So now once we did that, now we got this model, right? So we can actually print the model and check, and it has a lot of embedding inside. Now we can actually try to take a look at what will happen if we insert this to our model and check. So we're going to say input tensor equal to torch.long tensor x, and then label tensor equal to torch.y, right? I guess my X is a numpy array, right? So I have to turn this into PyTorch first. And once we did that, now we are ready to insert our thing into the model, right? So we're gonna try loss equal to model and input tensor. Let me just take a look what my forward function needs. So my forward function needs the center, the outside, and the all vocabs. So input tensor, label tensor, and then the all vocabs, right? All right. Okay. So now we print this, and there's no errors, which is a good thing. And then we print out the loss, right? So what I'm gonna do is just try to run this several times, right? And based on this loss function, it would try to minimize this, and eventually the center embedding and the outside embedding will be optimized. And in the last, we can actually look at this embeddings, which is the whole point of the Word2Vec algorithms. Okay, so I think we are pretty much done on the model. Is quite a little bit difficult, but I don't. You can pause my video and take a look, right? Okay, great. And let me just make sure everything is nice. So I can clear all, but restart and run all, right? And there's no error. Great. So the next thing is training. I think from here on is quite easy, right? So for the training, I can make sure that I'm very clear that my batch size is 2 and batch size is 2, right? I mean, for those who are wondering like why I choose batch size 2, there's no real reason. I just want to do that for this example, but you can play around with it and see what works. But our data set is very, very small. So I think this number is okay. And then model equal to Skipgram. I think it needs a vocab size and then the embed size. And then we're going to set the optimizer to be Adam, right? You can try with SGD, and we're going to insert the model of parameters and also the learning rate. Great. So this is done. The next thing we're going to do is actually running the algorithm, right? And here we're going to run maybe, let's try 5,000, right? I mean, we can do 5,000 algorithm epochs simply because our data is so small, right? So we're going to do for epoch and non-epochs, right? And range. So I think you guys can recall how do we actually train, right? So we're going to get batch, right? And right here, we're going to do predict, right? Now, of course, optionally, we can get the loss, which is already in the function of the prediction. And then we're going to do back propagate. All right. And then finally, we're going to do update alpha, right? Of course, optionally, we can print the loss. So we're going to do here, we're going to get the batch. So we're going to say input batch and label batch is basically equal to random batch function. And this is a batch size and corpus, right? And then we just have to input tensor equal to torch.long tensor. I mean, you can actually, I guess you can actually put this long tensor into this random batch. I just forgot to do so. So I'm just gonna do here, right? Label tensor equal to torch.long tensor and label batch. Right. So once we have this thing right here, right, we can now perform prediction, right? So the prediction is basically model and input tensor, label tensor, and we already have this all vocabs, right, that we already prepared up there. And then we can back propagate. Lost dot backward and lost dot step, right? I think optimizer does step. But I think that's one thing I may want to do this is optimizer. Right. So right here we can do optimizer dot zero grad to make sure everything is cleared nicely, right? And then, well, of course, we can print the loss, right? Yeah. So what I'm going to do is if epoch plus 1, and for every 1,000, all right? I think that would be nice. Equal to 0, right? Then plus friend. I'm gonna use f string here. Epoch. I think I named this epoch, right? Epoch, and I have to do +1, and then the loss is loss and 6F. I guess 2 in the front and 6 at the back should be enough. And yep, I think that should be it, right? So let's try running this and see there's no problem. Okay, great. So it seems like the loss is reducing. Why not we just try more and clear all the outputs, restart run all. And all right, so great. This doesn't look very nice. Let's try 6F. All right, great. So the loss doesn't go down much, but of course, you guys can try to play around, right? But the point is just to try to show you that this is a very simple way to train your embeddings. Great. So now we can actually plot the embeddings. So let me close down this one. I don't think we have to check below. So now we plot the embedding. So the real question right here is fruit really near to banana, right? And in that case, it's fruit really far from cat, right? Something like that, right? That is what we want to check. If we have successfully trained this, then we should see that, right? But I'm not sure, since simply because my data set is pretty small, right? But of course, let us try this. So what we can do is we can maybe first of all list all the vocabs we have, and then let's turn first of all, let's turn our banana into torch tensor. All right, so now we have this banana as a number, right? And we have this surrounding it to make it as a common one, I think. And then we can embed it. All right, we take the embedding of that. So we're going to do model that so our model has actually 2 embedding, right? To access inside, we just do embedding center, all right, of banana. And of course, we're going to do the same for outside banana. And you will have this banana embed center and banana embed outside, right? And we're going to do this. And finally, of course, you guys can print it out. And basically, this is a learned representations of the banana, right? And of course, you can also print the outside. So what we are curious is whether if we plot it in a 2D graph, this is perfect for plotting. Sorry. This is perfect for plotting, right? Because I intentionally choose 2 so that I can plot easily on a graph, right? So now, now of course, the final embedding of banana is basically taking this one, right, plus this one divided by 2, right? So that would be probably a very nice representation of banana, right? But before anything else, why not I just create these functions, right? Because I don't want to do this repeatedly, right? So I can create a function called given any words, I'm going to get the embedding, right? So get the embed of any given word, right? So firstly, I'm going to say that try to get the index of this word, right? And if it doesn't have, then the index is simply, I would say, Ank. Right, and I don't think this is a function, this is a dictionary, right? So this should be like this. Great. This is just to prevent we don't have that embedding of the word. And then we're going to turn this into long tensor according to this. So I'm going to just copy this, right? And this is word. And this is basically the word. Right. And for each of this word, we're going to get the center embedding and then divided by 2. So we're going to do this. All right. And yep, why don't we do this? Okay, give me 1 second. I'm just gonna change all this at the same time. Okay, great. And this one should be word. Word. All right. So I think we got a very nice, and this is finally the embedding. And then finally, we're just gonna return to be easily plotted later on, and also we're gonna just remove this tensor thing and remove all this bracket. Okay, so now we can do embed 0, 0, and then dot item. All right, and then embed 0, 1, and dot item. All right, which will retrieve this one to be here, and the second numbers right here. All right, which will be very nice for us to see. And we're going to return as a tuple anyway. All right, so now I think once we have that, now we can try to get embed of the fruit, right? So this is the number we have. And we can actually try, why not try get embed of what, cat, right? And then we try with sorry, why not we try with I don't remember what other vocabs we have, sorry. We have so we have fruit, right? Fruit should be near to banana, right? So let's try this, right? And so this is the banana and this is the fruit, right? So you can see that they seem to be closer to one another, and cat is pretty far away, right? Maybe we can see whether dog is actually near to cat as well, right? So you can see that dog is quite close to cat itself, right? But anyway, I think to do all this, I think why not we just plot it, right? And to see everything. So let's give me time to plot this. So plt.figure. Figure size, let's try like 6.3, and then we're gonna say for I, comma word, and enumerate all the vocabs, right? And x, y equal to get embed word. And then we're going to say plt.scattered xy. So it will dot perform a dot like a scatter plot on each of this dot. And then it also we say annotate so we know what is each word. So on word, and the position is basically at x and y. And then we're gonna give some xy text 5,2. All right, and then finally the text coordinates offset points. All right, And then finally, we're going to show this diagram, right? And this is basically what we have learned, right? And it looks quite promising, right? Even though our data set is very small, we can see that cat, animal, dog is very close by. And at the same time, apple, banana, fruit is clumped together, right? If we have a very big data set, it would have been much better, right? So, but anyway, as you can see, even with a very small data set, we achieve basically the objective, right? That is that any embeddings that is close to one another, they must be close. And at the same time, anything that is like completely unrelated should be like this, right? Great. So I think we are very happy with our end results, right? And please go back home and try to play around with this, right? Finally, let us try to do some cosine similarities. And to do this cosine similarities is basically very simple, right? So for example, banana equal to get embed banana. Right. And then we also have fruit equal to get embed fruit. Right. So what we need to do is basically dot product. Cosine similarity is nothing but just dot product, right? So to do that, we just simply do np.array banana. Let me just make sure it works. Okay, great. And then you just dot with np.array root, right? And you got a very nice number, 0.577, right? If you change this to, why not, we just tried one more, maybe cat, get embed, right? And if you try to dot with this, right, this will be supposed to be a very low number because it's not so similar, right? But if it's very closer to one another, then it will be a very big number, right? So let's try something like right? And just do that. And you can see that when you dot product, this number is really so slow, indicating that banana and Ankh has a very large difference. All right. So, yep. So that's it for the Word2Vec. I think you can please try to pause my video, go back and forth, and you should be fine, right? So Word2Vec is one of the most, I think, initial algorithm that is very successful. And because of Word2Vec, we have later on a lot of good embeddings that we have until now. All right. So please take a look. All right. Thank you very much.